tell Jake he didn't.
Remember, Jake wanted me to take this.
Oh, yeah.
Ask Chester Van, I'll forget. So here we are. We're at our first one here. We're going to be adding two resultant vectors using our tip to tail method of our triangle. So when we do these, you always have to have something to get your bearings about you. So what we do is we draw an x and a y axis, two perpendicular lines. So this is where we're going to start Tia. Tia is going to start at the origin. Now the directions that they gave us is that Tia is going to walk 50 degrees east of north. So this is that quadrant bearing. So we need to take our protractor, and I still am going to advocate that you always get your angle first. If you don't, you're never going to know where you want to travel in the first place. So we want to put our protractor on the origin, centered on that, and we want to go 50 degrees east of north. And then we're going to put a vector that goes from the origin, hopefully going through 50-degree angle, east of north. So we're in our first quadrant. Then we'll have to nail down how we want to scale it. So 1 centimeter is going to represent how many feet? We've got 120 and 80 to work with. 40 wouldn't be bad. Then we'd have vectors of 3 and 2. We might want to make it a little bit longer. I found that if you make it a little bit longer, they're easier to get through your protractors. So what's another scale that works pretty well with that? All you gotta do is find something that goes into 120 and 80 that's a little bit smaller. Rather than 40, jump down to 20. And even 10 would work, but then it gets a little bit big. So 20 was a pretty good one. Now, keep in mind, if you want to go with that other measurement, you sure can. You just have to indicate what it is on your graph. So now we got to measure how many centimeters on our line. I guess I should actually call it a vector. 20 goes into 120 6 times. So we're going to make this 6 centimeters long. Try to do this accurate as I can. Okay, not bad. So this had a quadrant bearing of 50 degrees. It has a magnitude of 6 centimeters, which represents 120 feet. Okay, now at this point she changes her direction. She changes where she's traveling. So at the tip of this vector, you really have to go and draw another quadrant axis on. Because from here, it's got to be exactly the same position as our first one. This is how we keep our bearing on the whole problem. Here she's going to work herself 80 feet due east. So where do we draw this vector? Straight to the right is a great way to put it. So from that spot, straight to the right, and now since it's 80, and 80 divided by 20 is 4 centimeters long. So now you got to make it 4 centimeters long. Now that's her position at the conclusion of this problem. It was nice that she went due east and didn't have to go measure another angle with the protractor. Now we're asked to find the resultant of this walk. So I'm going to pull it out of the way so it isn't hard to see. In order to find the resultant, I'm going to drag this blue line. Remember, it goes from the initial starting point to the terminal point of your second vector. So this blue line represents your resultant. Now basically what we did is we just added one vector, whatever you want to call it, vector u is typical, onto vector v, and we get our resultant vector. So vector u plus vector v should give you your resultant vector. So how do we know what our resultant vector is? We'll measure it. Okay, so my protractor, that was nice because I don't have to move my protractor. You had to take yours off and draw it. On this one, see how close your angle is to 65 degrees. The resultant vector is at 65 degrees east of north. So N, 65 E. Now you may get something a little bit different. Please record whatever you get. I was really impressed with first or third period. They had 66, 67. We were really close. Now that's how we get the direction. We also have to name the magnitude. But in order to get the magnitude, we have to measure. And we were really close third period as well on that. So (9.5). Alright. So the resultant is 9.5 centimeters. We have to take that times 20. So whatever 9.5 times 20 is, these calculations right, it's 190 feet. Okay, and that's underneath my ruler. So in the end, our resultant vector, here's what I'm going to summarize it as. Our resultant vector is going to be, parentheses, put the magnitude first, 190 feet, comma, and we're going to go 65 degrees east of north. That's typically how you're going to see your vectors summarized. This is what we ended up with. So from original starting point, you understand what that's all talking about, right? From where she originally started to where she finished, or where we said we're going to track her down, is here.
So we eventually stop drawing these up and start using straight lines. How do we do that with the anchors?
Oh, we'll get there.
Oh, it's just a triangle.
It's not a right triangle, but it's a triangle. So if it's not a right triangle, there are two methods that we can use. Perfect. That's what we'll end up doing. Okay. Now, go ahead. Here.
So it's U plus, or the factor U plus factor V is supposed to be 4.
It equals the resultant. And what is our result? Here. When you add vectors, you're going to have to reconcile the changes in direction and the changes in magnitude. Right, these next ones are kind of tedious, and you have to have your textbook. It's all the way it works. Because it says, find the resultant in each pair of vectors using either a triangle or a parallelogram method. So we're going to do just one of these. We're going to do 3A, and they're going to go down and do 3C. Because these are, yeah, there's not a whole lot to them. Okay, we're ready for this? Or are you still getting organized? Well, this whole thing is on page 482, so it's got to be awfully close to 483 or so. 485? Okay. Just puzzles me. Makes me angry. These things are supposed to be grouped together and never leave each other with accident. Are you already measuring this or something? Yeah, okay. Yep, always go to the end of the point. I'm going to drag this down. Every once in a while, that vector isn't long enough to go through your protractor, so how do you reconcile that? Yeah, just extend that line. I'm just going to use this to do that. If you extend that line through, then it makes it a little bit easier to try to estimate that angle. So, I don't know what it looks like to you guys. What are you getting for an angle measurement? Okay, you're measuring the length. So Jess has got the length nailed down. Anybody got an angle to compare with? Okay, so you think it's right at 50? I don't know what's wrong with mine then. Seems a little off.
Yeah.
Are you at 52, Cole? Yeah, if anything, I'd have been pushing a little bit more towards a 45, but I don't know.
We don't really have an axis to work on.
Yeah.
That's what you gotta do, you'll have to, okay, so can we use a 45 here? And
Yeah.
let's do this, let's make it a 45-degree angle, and let's measure the length of it.
How about I go 45 and then?
Fine, we'll go 48.
Critical.
I mean, I really don't, that's part of the human error experience that we're gonna have with this.
We won't get that when we're just using trig.
We will not, then we'll be able to nail it down pretty tight. And I'm kind of concurring with Jess, I really like that 1.8.
Yeah, we were at 1.2.
Okay, so now what we have to do, we have to recreate that on our axes. So you gotta come down here and you gotta measure your 48-degree angle that you wanna be on. And you also wanna make it so that it is, I don't know, 1.8. 45, right? Ooh, bugger. What's our scaling gonna be like on this? Do we really have to scale it at all? That was a question.
No, because we measured it.
Right, okay, so let's just go to our 1.8 centimeters. So there's a lot of kind of fooling around, especially if it's too on this. It's not the easiest to do this. Close, I guess. 1.8. Okay, so that's a little bugger down there. Yep. Okay, so now we gotta go back up to our second one. That was vector AB. This is vector B. We want to add on to it vector W. But what's really nice about vector W? It is due north. So we're going to go due north whatever the length of that thing is. So what do you have for the length of it?
1.2.
Alright, 1.2. Now remember, at the tip of your first vector B, you have to put in another XY axis to get your direction correct. So that's where, to the best of your ability, you want to make nice horizontal and vertical lines and make them parallel to your original axis. And then we're going to measure a vector that goes up. I forgot, 1.2. So now you got to get your resultant. Connect your initial tail to the final tip. Come on, be kind. Don't be so mean. It's pretty close. And now what do we do? We measure. And for crazy, I'm starting to get ticks. There we go. And we should be fairly close to each other as far as those measurements.
2.7 centimeters.
You like 28 degrees east of north? Oh, what did it say about it? Ah, bugger. All you gotta do is go with this. State the magnitude of the resultant to the nearest centimeter and the direction relative to the horizontal. So just relative to the horizontal means from what position? Standard. So, okay, so all we really need is to measure from here to here and the length of it. So I'll rotate this around. Yeah, you could have just subtracted it too. I'm getting really close to 60, which is kind of what you were saying. If you ran your 30, whatever. Okay, so now our resultant vector is going to be given as magnitude first. So what was the magnitude?
2.7.
All right, how do we like that? 2.7. You notice they just asked me to go to the nearest centimeter, wasn't it?
Yeah.
They say the nearest tenth or the nearest centimeter? Look at us. We're going to nearest tenth. We said 2.7. It's amazing how close we get, honestly. 2.7, comma, and then we have 60 degrees. And maybe I would do standard bearing on this, because it might be a little bit hard to know if you're doing. No, it wouldn't. It's got to be that. No, it's assumed that it will be true bearing, but I didn't use 0.60, so it should be pretty
So
self-explanatory.
if you do something like 220 degrees from standard position,
It would be awfully difficult to tell if that's true bearing or standard position, right? So that's where our directions come into play, and I put SP standard bearing on. Okay, I'm not going to do 3B because it's just more of the same. But I think the pinball one's kind of fun to try. So 3C, a pinball is struck by a flipper and is sent 310 degrees at a velocity of 7 inches per second. Then the ball bounces off the bumper and heads off at 0.55 degrees at a velocity of 4 inches per second. Find the resulting direction and velocity of the pinball.
How can you go through?
You think about those pinballs, think about your flipper down here, and you're going to be rotating it like this. That ball's coming down, you hit it, it can go off at a 310. Now, 310 from where? True bearing. Okay, so let me get some of this stuff out of the way, because it's kind of cluttering stuff up. True bearing is from where?
Oh,
Due north. Do we measure clockwise or counterclockwise?
right.
So we got to go 310 degrees that way. Now that's a little bit difficult when your protractor only goes 180. So how to resolve that?
Wait, how did we know it was true bearing?
Right here, 0.55. That was their key. They didn't say anything else because they're wanting us to remember it. You got 3 digits in there. Guaranteed that it is true bearing. So from here to here would be 270, and 270 plus what is 310? 40. So what we'd want to do is measure another 40 degrees. So right in there. Which should leave us with how many degrees short of 360?
Should be,
No, 360, not 380. 50.
310 should be 50 degrees short. So what have I done here? Oh, I didn't measure this very carefully. I got to go 270 plus another 40, so that would be here at 50. Now that all matches. It'd be 50 degrees short of 360. What do you think about scaling for this? 7 and 4, there's not a really good common factor. Can we measure 7 with the... You live with that, or you want to go halvesies on it or something? We can go halvesies and go 3.5 then. So I better write that scale down so I don't forget. So now we're doing 1 centimeter equals how much? 3.5?
no, 1 centimeter is 2.
3.5 centimeters.
So we're going to go 2. Does that work? Okay, so if it goes 2, I think that's what we want here, 2, and it's going to be inches per second because it's representing velocity. So that means we need how many centimeters on here to represent 7? Yeah, that's what we want. 3.5. Oh, this thing up on here. 3.5. You got to shorten that letter up. 3.5. I'm going off my 50 now.
No, it's 40.
think that's getting pretty close. All right, think of it one of two ways. If you go from here to here, Alexis, you're going to get 270. You want to get up to 310. You'd have to go another 40 degrees, 10, 20, 30, 40. Or back off 50 degrees the other way. So that's probably the better of the two plans, but it really doesn't matter. Okay, so that's where the pinball heads off, but first, after hitting the flipper. So now after it hits the flipper, it's going to hit a bumper. And what's happening at the bumper?
55 degrees.
Okay, so draw your XY axis at the tip again. We want a 55 degrees from true bearing. So we're going to slide this up. We're going to rotate it. Here's what I can get. Then 55 degree from there. We extend that out. 55 is somewhere in here. And now what would we use? 2 centimeters. And now we've got tip to tail, connect it with the resultant vector. So we're after the direction and speed of our resultant vector from true bearing.
Do you ever use true bearing?
Nope, not going to do it. Wouldn't be prudent. So, bring it back over here, put it on your original XY axis. How many degrees short of 360 is that thing?
16, 17,
Okay, we're looking 16, 17, mine's looking right at 15. So 15 degrees short, which means it puts us at a resultant vector of something comma 345 degrees. And all we need now is a good measurement. And then multiply it times 2. Anybody? Anyone?
I got 3.7.
3.6, 3.7. Dandy. 3.6, 3.7. I had a 3.8. Double it. 3.6 would be 7.2. Somewhere in that range. 7.2. And that is inches per second. Feel good? It's a little bit monotonous and tedious because you're sitting here doing all those, but we want to really get, and what I was hoping to get also with the hyperbolas, parabolas, and ellipses, if you fiddle around with things mechanically, with your hands and with the computer, you kind of get a better grasp of what's going on, and then we'll be able to sink our teeth into the algebra part of it, or true. I kind of a side note here, I didn't even talk about it, but see this one here? Parallel vectors the same direction. If you had two vectors going parallel with different magnitudes, what would the sum of this vector be? What would the resultant be? 5, just the sum of those. What if they're going in opposite directions? Then your resultant vector would be, if this 3 was going the other way, -1. It'd go a little bit to the left. This is like a tug-of-war deal if I turn it around the other way. I think that was all on that page. When you add two opposite vectors, the resultant is a 0 vector. Does that sound reasonable? They call it a null vector, denoted by, well, a 0 is a vector over it, or it looks like a bold 0, which has a magnitude of 0 and no specific direction. Should make a little bit of sense. Subtracting vectors is similar to subtracting with integers. They're saying there's some similarities here. Rather than subtracting a vector, you can add its opposite. And if you add its opposite, which direction is it going? The other way. So that's why we did that little bit with that opposite vector. So we only got one thing left here to do, and this is a scalar. This 2 is a scalar. All it does is it multiplies your length. It doesn't change your direction. So this 2b says take vector b and double its length. That's it. Don't change its direction. If you look over here at this one, 1/4 p, it says whatever the length of p is, take 1/4 of it and then add it on to, well, so add it on to a negative of it. So, right? We're going to try to do this ABC one. I don't know if we're going to get down to it. Depends on if you're going to stick around. Probably not. It's no different here, right? We got to figure out A, so we got to copy this one out of our book, so we got to figure out its magnitude and direction. So A has a direction of 40 degrees. It has a magnitude of 2.5. And this is really nice because this keeps that angle now. 2.5. Close. A little tail. Here's the only new part I really got to make sure that we do. We want to subtract C. Now C has a magnitude of, you can measure it and see. Can you guys grab that for me quicker than me? Can we call it, it could be a 1.9 if we really want to make it nice, a 2. Is that close? Okay. So it's got a magnitude of 2-ish. And what is its direction? Now I'm measuring these from standard position. I don't think they specify, so I like standard. I'm more comfortable there. And what would you say that direction is? If we want to make it fairly simplistic, what do you think they're trying to hit? 100 and... Okay, 115, that's fine. Let's try 115. So if this one is 115, this is the issue I want to make sure we're going to resolve. Now when we add this on, because we're not going to add or subtract C, we're going to add the opposite of C. So we want to keep the magnitude, but we want it to go the other way. So what angle are we going to put on this thing? So we got to come back this way, right? Because our 115, I'm just trying to think with you, that's your 115. Then you're going to add 180. Where does that put us? $295. Take your word for it. Here's what I'd like to try to do with you. Remember how I said you can do the negative direction? So if we would go the same, let me get another vector up here. What was the direction that thing was going? 115, right? Where's 115? 115. Now if I do that, and I simply extend that and go the magnitude of a negative, just extend this. God, do it again. Like that. And measure what? Negative, whatever we measure that was -2. So just measure down 2 from that point of intersection. And that's where it's got to be.
Oh, so you're saying just forget about measuring?
Yeah, see, I don't know why. Maybe I'm just partly dyslexic on this whole thing. But I have a hard time when I got to take that 115 and I got to get over here. You went 295, said, I'll take your word for it. So I'm going, dang, what is that thing? So I don't want to deal with that. So what I do is I just go my same angle, but then go the opposite direction. Get the deal? Now we got to go from there, and we got to add on 2b. So take your axis, go from here, and go 2 lengths of b. So we need this direction of b, which this can be pretty accurate this way, I think. I don't know if I like the way I'm really doing that, but see how I can measure that angle? If I were doing it right, I'd probably want to do like that angle, which would be 180 plus another 60, so 240. Or I just simply go another 60-degree angle past here. There's a lot of different representations you can make of this, but then make it twice as long as B.
It's about 2 centimeters.
It's about 2 centimeters, B is, double. Let's see, I don't have this last one, but anyway, 60. Then measure 2 centimeters, and then put your resultant back on that. Are we fairly confident we know what we're doing on that?
A question. They gave us like 15 vectors. We have to
That would be annoying. I hope they never do.
just find them one at a time, combine them one at a time until we combine them all.
Pretty much.
All I
Just
have
keep
left is the last
pecking away at it. Okay.
one. You can correct everything except for the last one.
Thank you.
You might have them done by Monday.
Blue. I think I'd have them done by the end of the day.
Awesome. Will you have them done?
Let me stop this recording. Measure the blue now. You're good. Stop.